Hi class, let me give you some hints on this assignment number 3. Okay? Just a reminder that the midterm is next week, but assignment number 3 is part of the midterm exam, so you still need to do this assignment number 3 while you're preparing for a midterm exam. Okay? So first question is to estimate the SE prime. Basically, if you recall that SE prime is the endurance limit under lab condition, but suppose that you don't really have the lab test results, and then how to estimate this SE prime. The idea is essentially to use the formula for SE prime, estimation formula, and this is the estimation formula for steel. So when SUT is less than 200 psi, and SUT is greater than 200 psi. Okay. First one is this much steel here, so you can look up the table SUT, which is 68 psi. Okay. This is hollowed here, so you can look at the table here. SUT is 112 psi, so fairly straightforward. But the number 4. This is not steel, this is aluminum. As you recall in the class, endurance limits, basically, this plateau, the phenomenon of plateau here occurs only to ferrous material, right? But for non-ferrous material, for example aluminum, you don't really have endurance limits, and the SN diagram just keeps going down. Okay, so basically for this one here, you don't really have an SE here, so there's no. Okay, and this one here is the 4340 steel here, and with tensile strength of 250. So apparently this is greater than 200, so this should be just 100 here. Okay, second question. It's also fairly straightforward. Just exercise looking up tables for marine factors. Okay. You don't need to look for all the marine factors. Let's say for this example, what do we need? This machine's finish, so you need this KA, and there is this size. Okay, so you will need KV. And last 4, there is a reliability, so you will need to look up the table, okay, for KE. So that's pretty much all you need. Okay, the 3 factors, and if you can find the 3 one, SE equal to KA, KV, KE, and SE prime. Right, the others just take it as 1. Okay, so it's very straightforward. Just one one thing that you gotta be careful here when you calculate KB. This is a millimeter, so use the formula properly for the KB. Okay, so KB is supposed to be this guy here. Okay, so number 3. It's a little bit complicated here. There are a lot of factors we need to look up to here. Okay. But first of all, there's a notch here, so we're going to have to actually consider that fatigue stress concentration factor. Okay. First step, right, is to get SE prime. The question gave you is this much material, and you can see that SUT, you look it up from the table, is 440 megapop, so 220 megapop here. Okay, so before we go ahead and find out the marine factors, we can try to find the stress concentration factor. Okay, fatigue stress concentration factor. Fatigue stress concentration factor. Now this question, if you look at it, it's a purely reversed torque. Okay? So basically the loading is the torsional loading. Then the fatigue stress concentration factor we're looking for should be TFS. Okay? Yeah. In the lecture we learned TFS, okay, is related to the stress concentration factor, static one, by this relationship. Okay. So Q shear is notch sensitivity, right? KTS. Okay. So basically, what we need is we need to find this and that. All right. So for Q shear, we can use two different methods. One is use a table, a figure, and the other use this formula here. Okay, use this formula. So we're going to use this formula to find the Q shear. Okay? Because the reason is I'll give you an Excel template, so you can use Excel to help you to do the calculation. I'll show you that shortly. Okay. All right. So first of all, you know what are each one of these here? The square root of Ka, we call that a Newberg constant. Okay. So Newberg constant here. Okay, so there are two different formulas for Newberg constants. One is equation 6-35a, the other is equation 6-35b. So this is equation 6-35b. This equation is used for torsion of loading. Okay. 6-35a is for bending and loading. R here is the fillet radius here. Okay. So the fillet radius is 2.5 millimeter. So that's already known. So what we need is just calculate this root A, the Newberg constant. Now this formula 6-35b. This formula is for SUT with a KSI. Sorry, this is for SUT with meter per unit. Okay, so SI unit here. But this question given is sorry. Sorry, this is for KSI units, right? This is for KSI unit here, okay? But this question here is a standard unit, okay? So millimeters is all standard unit. So we have to modify the question slightly here, okay? In order to calculate the Newberg constant correctly. So what do we do is basically we convert SUT into the standard unit by dividing 6.89, so that basically we convert that into PSI now, right? So this is convert. So this is from negative part to PSI. Okay? And we also multiply this much here because the unit over here is the root inch. Okay? The unit here is root inch. So what we need is we need to basically convert this guy here into a root millimeter by multiply this guy here. So this basically gives us a root millimeter unit. Okay? Yeah. Those formulas you can find this one in my lecture notes. Okay, so and in the Excel template that I give you, I have already entered this formula, so you'll be able to basically shorten your calculations. Okay. Yeah. So anyhow, if you plug in corresponding values, you will be able to calculate the Q shear is approximately 0.8, right? So, and I'll come back here. We also need to know the KTS. So KTS here. KTS, you can find that from the table, from figure. I'm going to show it here from figure 8-15-15. Because the 8-15-15 is the kind of a loading condition, the same as the current question. So that's the 8-15-15. Try to use properly the proportion, the dimensions, okay, as listed in the question. Find the ratio, and the KTS is about 1.4. So once you get the KTS and substitute it here, you'll be able to get a KFS, and that's about 1.32. Right? Okay. So that's fatigue stress concentration factor. Okay, so now let's we need SE and SE prime. So what factors do we need for this question in here? First of all, we need a Ka, surface factor. Take a look at this question here. This is a cold drawn steel, or machine. Actually, there's also says the radius machining to it. So we should use the machine surface, right? So you can find a Ka. You also need size factor Kb. Okay. Kb here. So you're going to use at least 20 meter here. Okay, this is the D here, 20 millimeter. However, okay, now the question says this is not a rotating bar here. See there? Yeah, so the bar is subject to purely reversing torque, right? So the bar actually here, the bar is a non-rotating. Okay? It's a non-rotating bar. If it's a non-rotating bar, if you recall that, okay, technically your KB, show you what's the KB. KB was D over 7.62. Okay. Like this, right? Like this. Okay. Yeah. Okay. So if you in the lecture, if you remember, we use this formula for two different kind of situations. One situation is when this bar is rotating, okay, and subject to a constant loading, right? Okay. The second condition is we can also use this same equation when this is non-rotating, okay, but if this is a reverse torsion. So basically, that's the condition of this question. So your KB is basically will be just 20 over 7.62, okay, like this. Okay, yeah, that's KB. Okay, so this torsional loading at here, so the loading factor Kc, right? This loading factor. If you look at the textbook lecture notes, you know that this is going to be 0.59. Okay. Temperature factor. Okay. For the first portion, part A, okay, the Kb temperature factor, just suppose it's the room temperature, so we have to set it to 1. Okay, but the second part of the question, we actually will have to use a different Kb. Okay, for the second part of the question. The second part of the question says now you have a temperature 450 degrees. Okay. Okay, so now that's all the factors that you need. Okay, so then you can calculate your SE, okay, based on the formula. So Ka, Kb, Kc, Kb, SE prime. So you should get 105.3 megapop. Okay. Okay, so the question asked is to estimate, okay, the number of cycles, estimate the number of cycles to failure, right? So what do we do with number of cycles for failure? In the lecture, we learned that to estimate the number of cycles failure, so we use the formula n equal to sigma A over A, okay, and then 1 over B. So where the B equal to nearly 1/3, okay, log F SUT over SE, and A equal to F SUT square over SE, right? Okay. However, this formula is for bending, okay, completely reverse bending stress, okay, situation. But the question here is torsional loading. So we need to modify that formula slightly, so basically sigma A should be replaced with the tau A. And what else? The SUT should be replaced with this SUT's ultimate tensile stress should be replaced with ultimate shear stress. And we have this relationship, okay, and that's equation 6-54. Okay. This is equation 6-54 in the textbook. Okay. So, and that's basically what we need to do, okay, to do all the changes here. Okay. So then the question, what is the tau A then, right? It's torsional loading, it's reversed. So tau A, so the magnitude of torque, okay, is T is given already. Okay. Torque, so pi d cubed, right? So basically this is from TR over J. Okay. But there's notch there, so we need to multiply our fatigue stress concentration factor with this guy to calculate the actual tau A. So you should get this is from the 68 measure plot. Okay. So now we got tau A, and the B here, SUT replaced with SU. Okay. Same for the A out here, calculate B and A. Plug it in, and you calculate the N there. Okay, so the N is approximately, okay, this much. Okay. Okay, so here's the Excel template that you'll see. Okay. Basically, I have every information here, but all you need to do is plug in the correct numbers for one particular question. So here's to calculate the surface factor. Here's the size factor here. So this parameters is all in standard units here. Okay. In the future, I'll also give you another template that you can use it for inch series for U.S. standard. Temperature. So we use a formula for calculating the temperature factor. Reliability. We can look at tables to calculate SE. Notch. Okay. Newberg constant formula. So use the right formula here. As you can see, the current formula entered here, right? That's the one I just showed you in the video there. And PT, and that has to be from the table here. Well, the table in our textbook, you know, basically it's a little bit different here. The curve is still the same thing, but you need to basically look at the table and find approximate. This table is from Norton's reference book. I recommend it. It can actually give you a curve-fitted equation. So I can actually use that equation to find more or less more precise numbers, right? Instead of looking up the tables. So in the end, we can calculate the A and the B. Okay? And we can do the calculation of these number cycles to failure. All right? Yeah. So. Look at that Excel, okay, and to get comfortable with it, you probably will be able to use that in your design project. Okay, so that's the first part of the question. The second part of the question is very easy now. The only difference is the TD is not 1 anymore, because now we have a different temperature. We can look at the table 6-4 or use formula, but the formula, remember, the formula is for Fahrenheit. Okay, the question here is the Celsius. So in this, update the SE, okay, and then calculate the N again. So now this time the N is smaller now, okay, because you got a smaller kg value. Okay, so this is the number 3 question. Okay, the number 3 question is basically when you're under torsional loading, how do we estimate the number of cycles to failure? In our lectures, most of the time what we deal with is a bending normal strips, right? Okay. Torsional kind of load. Number 4, okay. this one here, very similar to number 3. So SUT first, okay, same material as number 3, then SE prime. Okay, so this one here is axial loading. So the marine factors that we need, surface factor. I think it's the same kind of surface, cold drawn. Okay, so cold drawn basically the machine surface. Okay. Ka, and you need the Kb, it's the size factor. Yeah, size factor. But this is axial loading. So if you recall that under axial loading, your size effect is can be neglected. So Kb is 1. Okay? Then the loading condition, because axial loading, so 0.85. Okay? And that's all you need. And you calculate your SE, okay, Ka, Kb, Kc. Okay, so once you get this, then you need your Kf, fatigue stress concentration factor. Because there is a hole right here, so fatigue stress concentration, the stress will concentrate on the top and the bottom here. That's the location where you're going to see the maximum stress, because stress concentration. Okay, so fatigue stress concentration says this is the normal stress, so it's Q times Kt minus 1, right? Okay. Again, you can use either table or formula to calculate. Okay. Either one of them, right? Yeah. Look up the right table, look for this kind of loading, you will find the Kf. It's about 2.23. Alright, so now we're ready to calculate this sigma A at here, okay? Sigma A. Okay, so the question here is, okay, let's see. Estimate largest force Fa that can be applied in Morin Coulomb action, okay? So what we need is we need this calculate the amplitude of sigma A. Sigma A equal to Pf Fa over area, and this area should be the net area, at this cross section here, right? At this cross section. Okay, so we don't know what Fa is yet, so we can leave the Sa as it is. Okay. However, we do know is the safety factor is given as a 1.8. Okay, so then the question is, if we're designing for infinite number life, okay, if this is designed for infinite number of life, so what does that mean? It basically means we are comparing the sigma A with the endurance limit. Okay, this is completely reversed stress. Okay, so we comparing SE, okay, with the sigma A, and we make sure that this value is greater than 1.8. All right. Yeah. So the boundary will be what? SE point over this. Let's see. We try to look at the boundary values, right? The critical values here. All right. So sigma A is that formula. Okay. And A is the cross-section area. So basically 60 minus that 12 diameter, okay, and times the thickness. There we go. You calculate Kf. SE is already calculated, then you can get this Fa here. So the Fa is about 20.1 kilonewton. Okay. Technically speaking, what you also need, this is for fatigue, right? This is fatigue loading. But technically speaking, what you also need to look at is probably what you also look at is, do we have a general yielding under the static consideration here? So if your static loading value is Fa, Fa is a maximum value, right? So basically here is the Fa, so here is the maximum value here. If your static loading is the same as this maximum value Fa, will that cross section fail or not, right? Okay. So when this is ductile material, if you use a maximum shear stress theory, or this is G theory, it doesn't really matter. It's all in the first quadrant there. So what you're really looking at is, Fa over the area, right? Should be less than the SY over NY, okay, the safety factor. So this is the yielding safety factor. So let's say maybe if I use the same safety factor 1.8 here, then the critical boundary will be FA over A equal to SY over 1.8, right? And you can solve f of A again for this equation, which is basically static loading condition, right? And that the FA turned out to be 98.7 kilonewton. So this is the maximum that you can use under static loading, and this is the FA maximum you can use under fatigue loading condition. Okay. Apparently, you're going to use the max this guy here because it's bigger than that. So this is going to be your choice here. Okay, the maximum loading condition. Okay, so number 5. Okay. Number 5 right here. Number 5 is more of a design question, okay, because you're giving all the loading conditions, the shaft layout, and then you're considering as what is the minimum shaft size, right? Okay, that you can use to satisfy all the conditions over here. Okay, so the question gives you the shaft the rotating shaft at this much speed, and you're looking for a life of only 3 minutes. Okay, so what we need is the number of cycles, during that amount of time there. Okay, so the life, the number of cycles is basically speed, okay, times the minutes, okay, which is this much of the number of cycles. Okay. The material is given, so you can find SUT, okay. You can also find SY. Okay, so then we can find our SE prime. Okay. Alright, so we will need basically the fatigue stress concentration factor. So we will need the KF. Okay. Same approach as you did in the previous question, right? So for this KT, you have to look at the figure A-15-9, okay, for that type of loading, okay, because this is basically bending. You're looking for the bending kind of a loading condition, right? Okay. Alright, so the other thing is, okay, before we move on here, the Q, okay, so this is the Q here, Q, that's also doable. You can find a Q from either the equation or from the formula, okay? So Q ended up to be 0.87. Okay. So TF is going to be 1.4959. Okay. If there's any differences, decimals, that's fine. Okay, so what else? And I guess the other question is, before we do that, the other question is, when you design for critical for the diameters, right? You design for the diameters. The question is, where is the critical location? So find a critical location, because that's where the diameter, the minimum diameter should be determined. Now, if you draw a bending moment diagram, apparently, that's going to be maximum at this location and 0 at the 2 ends here. So maximum bending moment occurs over here, right? Yeah. However, because the stress concentration, chances that the critical location is actually going to be over here, okay? Because the stress concentration. So what we need is in this case, we're going to just look at the fillet location over here, okay? Fillet location. So in other words, we need to know the bending moment at this fillet location over here. So what does that mean? And equal to it here. So a shortcut is you don't really need to draw out this bending moment diagram across the whole shaft. You can look at this because equilibrium. So the bending moment at this location really is just R1 times 12 inch, right? Yeah. So the M basically is R1 times 12 inch. So what is R1 then, right? R1 is the point force here, R2 is here, and they need to balance this force F here. So the way to calculate R1, there's another quick way is equilibrium. So the force F, okay, the moment generated by force F at this location should be equalized or should be equivalent to the moment generated by R1 at this location. In other words, this force times this distance should be the same as R1 times the whole length at here. Okay, so having said that, that basically means the R1 times whole distance, whole length, which is 24 inch the shaft, should equal to F times the other distance times 6. Okay, so what does that mean? That means R1 equal to F times 6 over 24. Okay, and then you times the 12, that'll give you a bending moment, right? Yeah. And F in this question is, how much F is? A 10 kip. So F is 10 kip. So 10 kip is 10,000 pound force. So now you get your bending moment, okay, which is this much at the fillet location here. Okay, fillet location. Then what we need is we need the stress, okay, at that location there. Okay, so sigma A equal to the fatigue stress concentration factor times M times the half of the diameter, the critical location, and over I, right? So this is the top one here. That's where the maximum bending normal stress is. So M, PF, every parameters you know, okay, except the D, right? Except the D here. So we can't have this without the D then, right? Yeah. Okay, same thing that you can, before we move on here, so let's say this guy here is a function of D. Okay, so what else are we missing here? Right. So we need SE. Okay. So for this one particular question here, you only need the two marine factors, just the Ka and the Kb, okay, K and Kb here, and then times Se prime. Okay, the other ones that you can consider, they're all just one there. Okay? So this gives you approximately this much here. Okay, so that's Se. Okay, so time to put things together now. Okay. And we're designing for a safety factor, okay, NF, and the NF value needs to be, so NF, right, needs to be NF needs to be 2. Okay, or in other words, basically, if you selected a diameter that turned out a safety factor greater than 2, then that's fine, right? Yeah, but safety factor needs to be at least 2. Okay, so how do we calculate the safety factor, right? In this particular case, you have actually, you look at that, you're only designing for how many number cycles, this much number cycles. So you're designing for a finite number of cycles here. Okay? So if you're designing for a finite number of cycles for completely completely reversed, okay, stress or loading, okay, my safety factor calculation should be the fatigue strength over the amplitude of this stress here. Okay, that's what you do. Okay. In the next few lectures, we're going to learn combined loading or fluctuating loading, basically not completely reversed. Completely reversed meaning, you know, back from mean and max magnitude are the same thing, right? But in the next few lectures, we're going to learn fluctuating one there. Okay. Under that condition, you can't use this anymore, right? We'll have some other design equations. Okay. So for now, okay, this is what you're going to calculate here, right? And you know that this has to be minimum has to be 2 right here, right? Yeah. Now, what about SF, right? SF. SF is the limiting, basically, it's the limiting fatigue strength under this condition. If you remember, the SF is related to the number of cycle by this formula here, A times N to the power of B, and A equal to F SUT squared SE, and B equal to 1/3 log F SUT over SE, right? Okay, so in other words, F here is a fatigue strength factor, and then we said in this question just use 0.9. Okay? So we can calculate this Fs given the number of cycles here. So that should be calculated about this much. Okay? And what we need is our calculation of safety factor, as I showed there, is SF over sigma A. Sigma A is the function of the diameter here. So the calculated value right here needs to be greater than 2. Okay, so here is where you're going to have to use the approach here. For now, we're going to use this so-called trial and error approach. Okay. Trial and error basically means, okay, so here's a D here. I'm going to plug in a D, a certain number of D here, calculate sigma A, and plug it here, check if the safety factor is greater than 2 or not. If not, then we'll just have to bump up the standard D, do it again, right? So, here's what happens you can do. Okay, trial number 1, we can choose D, okay, as I suggested. I didn't suggest anything, but how much did I start with again? Oh yeah. So I started, right? Start D with 2 inch. Okay. You plug the D, you put 2 inch into the sigma equation over there. Okay, sigma equation. Okay, and then plug it here. Okay, so then the calculate sigma A is how much is going to be 60.7. Okay, then you use this SF, okay, over sigma A, and it will turn out it is only 1.47, and that's less than 2. Oh, sorry, actually in this question not 2. We're talking about the desired one is 1.6, right? 1.6. Okay. So it's less than 1.6, which means that D equal to 2 inch is not big enough, right? So we need a bigger size here. So then trial number 2, we start D, bump the D. Now here's the trick. So how do I bump the D here, right? The rule of thumb is we're going to use the standard size. Okay? The standard size that can be looked up from table A-17. Okay, so the standard size, there's some fractions standard size, there are some inch standard size, there are SI standard size, decimal standard size. So this is a number given in the decimals as the standard size 2.25. That's how much we can bump up. Okay, standard size basically is the size you can get off the shelf, right? Not a customized size. If you try this new D, you'll find that the new safety factor will be 2.1. It's just greater than the desired 1.6 now. So that satisfies the condition here. Okay. I did ask you to use an Excel for this question to facilitate the calculation here. So this is what you're going to see in Excel. I probably deleted a couple of the formulas of cell values, and you have to fill in the blank there. Okay, but in essence, basically, you get different trials here, okay, and do the calculation, you get the safety factor. Okay. So other than that, each cell, given the meaning of that, they're pretty straightforward, right? Yeah. So in the future, okay, when we learn shop design, okay, we're actually going to use a better design approach, particularly for selecting the size D. So instead of this trial and error, we are going to use a more sort of automatic process. Okay, it will let the D converge to a desired value. Okay, so stay tuned until the shop design course, and I'll give you different ways of solving for diameter D instead of trial and error. Okay, so good luck with your midterm, and please review thoroughly of all the lecture notes, tutorial notes, assignment questions. Okay, the assignment, the midterm is closed book, but you can bring formula sheets. That's all for this hints here. Thank you.